People read the plus or minus on a result and treat it like safe wiggle room. Then they approve treatments or ship features that turn out not to help at all. The mistake is believing that a confidence interval is the probability that the true effect lies in that specific range for this specific sample. What actually happens is that the interval is produced by a random procedure that succeeds at a certain long run rate, and overreading it turns a frequency guarantee into a single sample belief that the math never promised. Picture yourself skimming a report, seeing a neat line with a center and a margin, feeling done, and only later facing questions you cannot answer when the decision fails quietly. Here's what that plus or minus is trying to say. You have an estimate, like an average difference or a proportion, and you have uncertainty because sampling shakes that estimate from one study to the next. A confidence interval is a rule for building a range around the estimate such that if you repeated the whole sampling process many times and used the same rule each time, that range would capture the real value often enough. The range is not a crystal ball for this one run. It is the output of a method with a known long-run hit rate. Say you see the phrase 95% confidence next to a range. The promise is about the procedure. If you could run many parallel worlds with fresh random samples each time, the rule would produce intervals, and about 19 out of 20 of those would include the true value. Your one interval is either covering or not. There is no additional probability about it given the data you already saw. The guarantee lies across repetitions, not inside the single interval you hold. Think about a survey that asks a simple question of a slice of the population. You get a proportion from those who responded, and the report prints a center with a plus or minus margin. The plus or minus is not a claim about your personal chance of being right today. It is the statement that you used a method that would capture the population proportion often enough if you kept drawing new samples the same way. The beginner mistake is to point at the printed range and say there is a high chance the true value is within it. That is not what was proved. The cost of that mistake is that you start mixing up what the method can promise and what the data can tell you right now. So you trust intervals that were built under assumptions you did not check or conditions you did not meet. You end up acting as if an imprecise study nailed the truth or as if a borderline result is a win. The correct way to think about the mechanics is this. Your estimator has a sampling distribution, meaning if you could repeat the sample over and over, the estimate would jitter around the true value in a predictable way. The typical size of that jitter is the standard error, which you can compute or estimate from the data and the design. The interval takes the point estimate and steps out by a few standard errors in each direction, where the step size depends on how much coverage you want and what distributional shape you assume. The design of the interval, not the specific data alone, is what creates the coverage guarantee. If your sample has very few independent observations, like a test that only gathered opinions from about 100 people, the standard error is large, and so the interval is wide. That is not an annoyance to shrink by rhetoric. It is the method telling you the study does not pin down the value very tightly. If you hate the width, the solution is not to talk it away but to collect more information or use a design that reduces variability. The plus or minus is a mirror for your uncertainty, not a public relations problem. Another way people go wrong is by using an interval formula that assumes simple random sampling when the data came from clusters, panels, or heavy non-response. That mismatch quietly shrinks the standard error on paper, and the interval looks crisp and narrow, while the real uncertainty is much larger. The practical cost is that you make confident moves in messy settings where confidence is not justified. The fix is to respect the design. The actionable correction is straightforward. Match your standard error to your sampling and modeling choices. Use cluster-aware or robust methods when observations are not independent, and when that is hard, use resampling like the bootstrap that can mimic the data structure. Check stability. Rerun the interval under reasonable alternative specifications and see if the conclusion holds or not. If different plausible routes give wildly different ranges, the honest interpretation is that the data are too thin or the model too fragile. Interval width is a negotiation between three levers: how much scatters in the data, how much information you gathered, and how demanding you are about coverage. More noise or less information stretches the range. Asking for higher coverage also stretches it. That is not a philosophical point. It is the math of sampling variability. As a decision maker, you choose the lever to pull. Accept a wider band and act cautiously, or buy more data and narrow the band before you act. Sometimes you care only about establishing that a quantity is at least above or at most below, a threshold. A single-sided interval focuses the coverage guarantee in the relevant direction and stops wasting width where you do not need it. This is appropriate when the decision is directional, like proving a medication is not worse than a standard by more than an allowed margin. Choose it up front. Choosing it after looking at the database in bias. Symmetric plus or minus is not always the right shape. When the sampling distribution is skewed, especially with small counts or heavy tails, a symmetric range around a mean can claim precision on the wrong side and miss where the uncertainty actually lies. Use methods that respect asymmetry, like transformations that stabilize variation or percentile-based intervals from resampling. The point is not to be fancy, but to match the shape of your uncertainty. Another silent trap is looking at lots of intervals and highlighting the ones that exclude a value you dislike. If you fish long enough, some intervals will look decisive just by chance, and the promised coverage no longer applies to the way you selected them. Guard against that by planning which intervals you will examine, adjusting thresholds when you look at many things, or using hierarchical models that share information across related estimates. The cost of ignoring this is a table full of false wins that will not replicate. Do not confuse a confidence interval with a prediction interval. A confidence interval is about a fixed but unknown population value, like the long-run mean effect. A prediction interval is about a future observation, which varies from case to case even if you knew the population value exactly. Prediction intervals are wider because they account for both your uncertainty about the center and the natural spread of new cases. If you want to say what a typical next outcome might be, you need the predictive version, not the confidence one. Also, do not mix up frequentist confidence with a Bayesian credible interval. A credible interval uses a model of prior beliefs updated by data, and it does let you say there's a certain chance the parameter lies in the interval, given the model. That is a different question with different assumptions. If you see an interval in a probability statement, ask which framework produced it, because the words sound similar, but the guarantees are not the same. When you read a reported interval, interrogate it. What is the target population, and what was the actual sampling process? What estimator was used, and does the standard error reflect the design and the data realities? What coverage level was chosen, and would a reasonable alternative change the decision? If any of those pieces are missing, the tidy plus or minus is not enough to trust. When you compute an interval, be explicit about your choices. State the parameter, the estimator, the method for the standard error, and the coverage level, and show the sensitivity of the interval to plausible modeling changes. If you're working with messy observational data, prefer design-based or resampling approaches that make fewer shape assumptions. If you are modeling, check residual patterns to see if the assumed distribution behaves, and adjust if it does not. The most common beginner habit is to treat the center as the answer, and the plus or minus as an asterisk. That habit costs you because the interval is often the only thing in the analysis that tells you whether your estimate is actionable. If the interval straddles both helpful and harmful values, you do not have a decision yet. If the entire range lives on one side of a practical threshold, you do. The shift you need is to stop reading confidence intervals as beliefs about this single line and start reading them as the trace of a repeatable method with a stated long-run reliability. The line you see is a product of that method, and your job is to check whether the method and its assumptions actually fit your data and your decision. Next, we go to type 1 and type 2 errors, the two ways every test can fail, because once you can read an interval, you need to see the two fundamental failure modes of decisions built on tests.